Okay. Hello, nice to see you.
Hello.
Yeah, you're right. So we, I mean 7 p.m. Our local time in Nur Sultan.
Okay.
Okay, cool. Then we will discuss a bit some details.
Yeah.
Okay. So today we continue our work with AC circuits, and this will be in particular this RLC resistor, inductor, capacitor electric circuit. So our goal is to understand what will happen when we apply some AC power supply to such an electric circuit, which contains resistor, inductor, and capacitor connected in series. How we can calculate electric current and also delivered power to such circuit, and hopefully we'll have enough time. At the end of the lecture, we will consider the resonance effect in RLC circuit. So let us proceed with this, and I will switch the camera. Okay. So we will consider such electric circuit. This is AC power supply. Then we have resistor, inductor, and capacitor. So here we have AC voltage, delta V maximum times sinus omega t. Here we have delta VR, this is resistor R, inductor L, capacitor C. So here we have voltage drop delta VL and delta VC. Okay, so from previous lecture, we know that this voltage drops over different components of electric circuit will be expressed by the following equations. Delta VR is I maximum times R sinus omega t, or it will be delta V maximum times sinus omega t. So this is actually the same voltage as we apply. Then delta VL is equal to I maximum times XL, inductive reactance, times sinus omega t, and here plus pi over 2, because we have phase shift between current and voltage. And this can be represented as minus delta no, here we will not. Minus will be for a capacitor. So it will be delta VL times cosinus omega t. Then delta VC is equal to I maximum XC sinus omega t minus pi over 2. And this is equal to minus delta VC cosinus omega t. So we have expressions for all components, like voltage drops over all components of the electric circuit. And obviously now we can, so total applied voltage is just the sum of all these voltages, since all components are connected in series. And now we can show like Phasor diagram with phasors for voltage drop over each component, and also phasor for the current. So let me share the screen. So here we see phasor for the voltage drop over resistor, then phasor for the voltage drop over inductor, and that for the capacitor. There is no phase shift between current phasor and voltage drop phasor over active resistor, so they are in the same direction. However, there is a difference in phases. It's like 180 degrees difference in phase between phasor of voltage drop over inductor and voltage drop over capacitor. So what we need to do in order to get the total voltage over the electric circuit, we need to, in a vector form, add all these phasors. So first we subtract phasor delta VC from delta VL. We get the difference. So the resultant phasor will go upwards or downwards, depends on the initial values of these phasors. Then we have at 90 degrees phasor of voltage drop over active resistor. And from here, it's easy to calculate the phasor of our total voltage across the AC electric circuit, which consists of resistor, capacitor, and inductor connected in series. So this angle phi is the phase shift between current in this circuit and voltage drop over this circuit. So that will be definitely defined by values of resistance, inductance, and capacitance. Okay, so let us come back to our slide, and let us represent this in some quantitative form. So delta V maximum is equal, from that image phase diagram which we have seen on the slide, we can write that delta V R square plus difference between delta VL minus delta VC square. So this is how we calculate magnitude of the resultant voltage. Now, instead of this voltage, we can represent it as a product of maximum current and resistance, or inductive or capacitive reactance. So let us do it. Here is E maximum times R square plus I maximum XL minus I maximum XC. And this is square. Okay, this will be equal, so we can factor out maximum current. We will get I maximum times square root of R square plus XL minus XC squared. From here, we can express maximum current, I maximum, as the ratio between maximum voltage divided by this square root of R square plus XL minus XC squared. Or it also can be written in a shorter form, V maximum divided by Z. So Z is impedance, is called impedance, and it stands for the opposition of AC current flowing in electric circuits, which takes into account both active and reactive components of opposition to electric current in AC circuits. It would be, I believe it worth mentioning that impedance in this form, Z is equal to square root of R square plus XL minus XC square, is actually absolute value of impedance. Indeed, impedance is a complex number which consists of active Z prime and reactive imaginary component Z double prime. And in this case, when we have capacitor, inductor, and active resistor in series, impedance in its correct form should be represented as a complex number where we have active resistor R, which stands for the real component of impedance, then plus I is imaginary unit, so I is equal to square root of -1 times XL minus XC. So this stands for the imaginary component of impedance, reactive component, and this active component stands for the real part of impedance. So if we take absolute value of such complex number, we will get this expression. So technically, in this textbook, when it specifies that this is this is impedance, this is just should be understood as the absolute value of impedance, and that is what defines what AC electric current will flow through the electric circuit. Oh, another parameter which is very important is phase shift between electric current and voltage applied to the electric circuit. This is our phi. So this phi is determined as arc tangents of delta VL minus delta VC divided by delta VR. And in other form, we can represent it in terms of reactance and resistance. It will be arc tangents of XL minus XC over R. So this is expression for the phase shift. And from here, you already may see that in the case when we have XL larger than XC, our phase shift is going to be positive, and electric circuit will be called more inductive than capacitive. If we have XL smaller than XC, phi is smaller than 0, and that means that our electric circuit is more capacitive than inductive. And another extreme, like special case, is when these inductive and capacitive reactances are equal to each other, so they compensate each other. Phase shift is equal to 0, and electric circuit behaves like an active resistor without any reactive components. So next step will be to deal with electric power in such AC circuit. So for instantaneous power, we can write that it will be the product of instantaneous sorry, electric current times instantaneous voltage applied to the circuit. And that would be represented as I maximum times sinus omega t minus p times delta V maximum sinus omega t. So here we have instantaneous voltage applied to the circuit. Here is instantaneous current which is flowing through the AC electric circuit. So this will result in the expression of I maximum times delta V maximum times sinus omega t times sinus omega t minus phi. So this is expression for the instantaneous electric power delivered to the AC circuit. However, it is some complex function of time, and it's not commonly used in practice to deal with such instantaneous power. It's more convenient to deal with the average power, which is delivered to AC electric circuits. So in this case, we should take into account one trigonometry identity, which is sinus omega t minus phi could be represented as sinus omega t times cosinus phi minus cosinus omega t times sinus phi. So eventually, when we take this into account and substitute instead of sinus omega t minus phi, its identical expression, then we get the expression for the instantaneous electric power, I maximum times delta V maximum times sinus square omega t times cosinus phi minus I maximum delta V maximum sinus omega t times cosinus omega t and times sinus phi. So it will be times sinus omega t times cosinus omega t, and here we will have also times sinus phi. So now, in order to get average of this instantaneous power delivered to AC signal, we technically, since these are constants, so this is constant, this is constant. So what we need to find average of this function and average of this function. Maybe I will show them in brackets. So average of this function, sinus square omega t, we have already found during our previous lecture when we were calculating expression for the IRMS. So sinus square omega t as average for one period or more periods is equal to 1 second, like 1 over 2. And similar could be shown, actually it is already almost obvious for this function where we have product of sinus omega t times cosinus omega t. This product can be represented in the form sinus omega t times cosinus omega t is equal to sinus 2 omega t divided by 2. And so this is not average, it's just we can use this trigonometry identity. And we see here that we have sinus, it's not square, so it's just absolute value of sinus function, just with twice higher frequency than initial expression for frequency of the applied voltage. Means that this function goes up and down, so twice faster with twice higher frequencies than applied voltage, but it has during half of the period, it twice becomes positive and twice becomes negative. And since this function is symmetric, then average of this function over one or more periods, it will be just 0. So this second term, where we have this product sinus omega t cosinus omega t, when we calculate average power delivered to AC signal, will be equal to 0. So we will deal only with the first term. And in order to write it down, let's go to another page. So average power will be equal to 1 over 2 times I maximum times delta V maximum times cosinus phi. So where we actually, instead of sinus square omega t, use this 1/2 as an average value. And these are constants, so we don't care how they don't change with time. So we have average power in this electric circuit. Taking into account expressions for the IRMS and VRMS, so we remember that IRMS is equal to I maximum divided by square root of 2, and the same stands for VRMS, delta V maximum divided by square root of 2. So it's convenient to represent average power in terms of RMS values. So P average is equal to, so here we substitute I maximum with IRMS times square root of 2. We will have 2 square roots of 2. They will cancel out with this 2 in denominator. It will be IRMS times delta V RMS times cosinus phi. So we know now that this average power is defined by the product of RMS voltage and current. Also, there is this interesting parameter cosinus phi. So this is called power factor, and this cosinus phi from this Phasor diagram, which we considered previously, would be written as the ratio of active resistor to the total impedance of their electric circuit, AC electric circuit. So now let us substitute this expression in the expression for average power. I RMS times delta V RMS. So instead of cosinus phi, we put R divided by Z. So here, now we can rearrange it a little bit. It will be IR RMS times delta V RMS divided by impedance times R. And this part is equal to IRMS. So eventually we get an expression IRMS square times R. So this is equivalent to DC electric circuit, and shows that average power which is delivered to AC electric circuit is defined only by RMS current and active resistance. So that means that there is no power losses associated with pure inductor or pure capacitor in an AC circuit. So why it happens like this? Just because twice per period energy from the AC power source is initially accumulated in the form of electric and magnetic field in inductor and capacitor respectively, and twice per period it is returned back to the power supply. So if they don't have any like wires or like connectors, they don't have any active resistance, pure inductor and capacitor kind of accumulate energy from power supply and send it back twice per period, which means that average power which is dissipated on this circuit is defined only by active. It's that power which is Joule length heat which is dissipating at the active resistor R. Of course, this current, RMS current, will be defined by total impedance of electric circuit. So capacitor and inductor will make an influence on the average power by limiting this RMS current. However, there will be no energy dissipation at ideal inductor or capacitor. So this is such an important statement with this. And by the way, talking about cosine cosinus phi, when we have phase shift equal to 0, cosinus phi is equal to unity. So this power factor is equal to unity, and then average power will be equal just to product of I RMS and delta V RMS. So means that in that case, it will be the highest maximum possible delivered power to this electric circuit when inductive reactance and capacitive reactance compensate each other. So we will talk about this a bit later because that is specific regime of operation of such circuit called resonance. Yeah, actually we are coming to this point in any way. So then let us go to another slide and we will consider resonance in RLC circuit. So we know that IRMS is equal to the ratio between delta V RMS divided by impedance of the AC circuit. So it is said that some AC circuit is in the resonance when RMS current reaches its maximum magnitude at certain driving frequency. So this RMS will be frequency dependent parameter. It's a function of frequency. And at certain frequency, this RMS current will reach its maximum value. Operating regime under this condition will be called as resonance of this AC circuit. So as you already heard from me, obviously the RMS current will not be limited by the presence of inductor and capacitor in this circuit, only in that case when inductive reactance is compensated by capacitive reactance, since these guys are in opposite phases. So if their magnitudes are equal and they are in opposite phases, they can cancel each other. So this IRMS in more general form is represented as delta V RMS divided by square root of R square plus XL square. Oh, sorry, not square, XL minus xc, this is square. So obviously we see that IRMS will reach its maximum value when we will have the smallest possible denominator. And that means when this difference will give us 0. So at some frequency, which is called omega naught, xl minus xc is equal to 0, which means that omega L, which stands for XL, is equal to 1 over omega C, which stands for XC. And from this equation, we can, sorry, here we need to put omega naught, because this condition is true only at certain frequency, which is omega naught. And from this equation, we can express omega naught. Omega naught will be equal to 1 divided by square root of L times C. So now we have equation which calculates the resonance frequency of AC circuit, which consists of resistor, inductor, and capacitor connected in series. And which, by the way, keep in mind, because that's quite common equation used for solving different problems. And let us now calculate the average power as a function of frequency in order to show some feature. But maybe prior that, we will check one slide, like some image, which will be useful to discuss. Okay, I share my screen, and here on the left side, we see how RMS current depends on frequency. So at some omega naught frequency, which we already know equal to 1 over square root of L times C, this RMS current reaches maximum value. What is interesting that we still have in the denominator for the expression of this IRMS, we have delta V RMS divided by square root of R squared plus difference of square of difference between XL and XC. So since XL minus XC is equal to 0, there is square root of R squared. And eventually we get just resistance in the denominator. So in denominator we have resistance, and that's why obviously the maximum value will reduce with increase of resistance of our resistor. So we kind of limit this resonance peak value with the resistor connected in series to inductor and capacitor. This is very important because such resonant effect is widely used in different AC electric circuits, in radio receivers for tuning, but we don't want to have some unlimited increase in current at this resonance frequency. That's why, for instance, if we have just inductor and capacitor without resistor, then we will get 0 in the denominator because R is absent. And it will be some discontinuity. This peak will go to infinitely large number, like value for IRMS, And that could definitely damage some electric circuit. So always such resonators should be limited with the presence of some resistor. Okay, now let's come back to our slides and get some equation for the frequency dependent power. So we know that average power is equal to I RMS square times R. This is equal to delta V RMS divided by Z square times R. Instead of Z square, we can write its expression. We know what is the magnitude of impedance. It will be delta V RMS square times R. And here, instead of Z square, it will be R square plus XL minus XC square. So now we can focus our attention on this particular case. It will be XL minus XC square. This is equal to omega, omega L minus 1 omega C square. And from here, it's possible to show that this will be equal to L square omega square times omega square minus omega naught square, where omega naught square, we don't need square here, we just omega naught is equal to 1 over square root of L times C. So now when we substitute everything like this expression instead of this part, we will get average power as a function of frequency. So it will be delta V RMS square times R times omega square, R square times omega square plus L square times omega square minus omega naught square. Okay, so now when we have frequency which is equal to omega naught, so this difference gives us 0, then in denominator we have only R square times omega square. Actually omega naught square, because omega is equal to omega naught. But we cancel out here and here, and also cancel this square and R in the denominator and numerator respectively. And this part is equal to 0. So eventually it will be at extreme condition of resonance when omega is equal to omega naught. Average power is equal to delta V RMS square divided by R. Again, it's limited by active resistor. So its value of delivered power, average power to AC electric circuit under resonance condition will be also limited by active resistor. And another feature which is important, but maybe we can share first this slide again. So here on the right side, you see how average power depends on frequency. So it's not only that amplitude value changes with change of resistance, but also such a parameter, important parameter in some peak analysis, as the half width at the half height of the peak. So means this, you see this delta omega, this is the total width of the peak at its half height. So this shows how sharp peak is and how distinctive it can be. So that is important parameter because resonance AC electric circuits are operated under resonance conditions when we need to tune this AC electric circuit to some external signal. For instance, the most common example is radio receiver. We want to tune the AC electric circuit of this receiving component part of the radio in order to get signal and accelerate only, amplify signal only of certain frequency, which is carrying frequency for certain radio channel, for instance. So we want to be very selective, and selective means we want to have this peak as narrow as possible, because only these signal electromagnetic waves at this particular frequency will then create electric current in the our AC circuit and will be eventually delivered to the to the speaker of the radio. So we don't want to hear any noises from closely located radio stations, which are working at frequencies which are close to the that particular frequency we're interested in. And in order to avoid some noise, this peak should be as narrow as possible. So from one side, you want to have some limit of the RMS current under extreme this resonance condition. From other side, you don't want to put too large resistor in series to inductor and capacitor, because that will limit the selectivity of such AC circuit and will result in broader peaks that is not very practical. So that always should be some balance. So let us come back to the slide, go to another page, and there is such a parameter called quality factor, Q, and this is the ratio of resonance frequency, omega naught, to the width of the peak at the half height of this peak, delta omega. So delta omega can be represented as R divided by L, and that's why this quality factor Q is equal to omega naught L times L divided by R. So this is a parameter which kind of defines in at certain conditions of angular frequency, inductance, and resistance, what will be the ratio between resonant frequency and the width of the peak at its half height. So that quantitatively can be described and defined. However, the general message is that peaks should be as sharp as possible in order to avoid possible noises or some effects, undesirable effects on the extracted signal. Okay, this is pretty much everything what I wanted to tell you for today's lecture. Thank you very much for your attention. If you have any questions, you're welcome. We will continue on Friday with a lecture about transformers and some maybe AC filters for different power supplies. But definitely the key question to be discussed on Friday will be transformers, which can convert, up convert or down convert voltages in different AC electric circuits. Okay, thank you very much for your attention. Have a good evening and see you on Friday.
Okay, thank you. Bye.
Bye-bye.